round cylindrical insulator with a radius of 30 centimeters. It has a volumetric charge density of negative 80 nanocoulombs per meter cubed. That means this insulator has charge throughout its entire volume. We want to know the value of the electric field at a distance of 10 centimeters away from the center, at 30 centimeters from the center, and at 50 centimeters from the center. So, I'm not going to draw my cylinder very long because we only have a limited amount of board space. We know the radius of this cylinder is 30 centimeters. The first point we're interested in is a point 10 centimeters from the center. So to use Gauss's law to derive our equation, we need to look at the flux through an imaginary surface. So we need, number one, to draw a surface where the field would have the same value everywhere and where the field would be parallel to the area vector. So, as long as we're nowhere near the ends, what do you expect the electric field to look like? Well, in the case, since it's negative, in, but the electric field line should just be pointing radially inwards towards this cylinder. So if we draw our imaginary surface as a cylinder, then the field will have the same value everywhere on it. I'm going to call the length of it L, some arbitrary length. So what we're doing is we're equating our flux. We're going to find flux by taking E times A, and we know flux is also equal to charge enclosed over epsilon naught. So at 10 centimeters, A is the area of the Gaussian surface we've drawn. It's the area the lines pass through. Since the lines are pointing radially inwards, we only need the lateral side of this cylinder. The surface area of a cylinder is 2 pi r L. To find the charge enclosed by that, we're going to use the charge density. We know the charge density times the volume of that cylinder. We only need to know how much charge is in here. So if we take the charge density and multiply it by the volume of that little section, volume is pi r squared L. Charge over epsilon naught, we're equating the two fluxes. The pi 1r and the L cancel, pi 1r and the L. So our electric field is equal to rho r over 2 epsilon naught. We know that rho is negative 80 nanocoulombs per meter cubed. You'll want to put in 10 to the negative 9 for nano. R is 10 centimeters, so 0.1 meter. Epsilon naught is 8.85 times 10 to the negative 12 coulombs squared over Newton meter squared. Plugging that all in, we get E is equal to negative 452. This coulomb cancels with one of these. This meter cancels with one of these. The leftover meter squared cancels with those. Our units are newtons per coulomb. Now, getting the negative value just means that the electric field is pointing inwards towards the inside of our little surface we've drawn. Questions on getting that one? At 30 centimeters, this same equation is still going to work. The equation we have for inside, this equation will work as long as we're inside or equal to the surface. So at any point inside, that equation will work. So it will work for 30 centimeters as well. The difference is R is 30 centimeters. So 0.3 meters. So E ends up being negative 1356 newtons per coulomb. This equation will not work out at 50 centimeters though. Out at 50 centimeters, we have a different amount of charge enclosed. So out here, 50 centimeters away, we draw our little imaginary surface. When we look at E times A is still going to be the 2 pi RL, where R is 50 centimeters. The difference is the charge enclosed. It's still going to be the charge density times the volume, but we can't use 50 centimeters when we do the pi R squared times L, because the charge doesn't go all the way out to 50 centimeters. It only goes out to the 30. So when we do the pi R squared L, this needs to be the actual radius of the cylinder, the 30 centimeters for R there. This time only the pi's and the L's cancel. So the electric field ends up being rho big R squared over 2 little r epsilon naught.
I have a question. With your L's, wouldn't you have to set up your Gaussian sphere so that, or whatever object, so that it had the same height as your, or L
As your actual object?
Right.
No, because Gauss's law is not going to work near the ends. It's only going to work in the central region. But it doesn't matter what L is because L cancels.
Yeah, I just think visually, if you had to do that.
Yeah. The flux doesn't simplify to E times A at the ends because the electric field is not uniform over the surface. So that's why you don't want to go all the way out to the ends. Okay. So rho is negative 80. Big R is the 30 centimeters, little r is the 50 centimeters, epsilon naught is the same as it's been, 8.85 times 10 to the negative 12. Our electric field out at 50 centimeters. Does it make sense that it has dropped? It was higher at 30 centimeters than at 50. That's because we're getting further and further away from the charge. Please keep in mind, I do expect you to know surface area and volume of basic shapes like cylinders and spheres, cubes. So those aren't on the test notes.